Okay, let's continue on with partial sums of a geometric sequence. And it is also given in this formula. So it's somewhat similar to the arithmetic, but not quite. If you want to think about it, this one has a power in it, an exponent in the geometric, while the arithmetic does not. Again, you're going to need to remember these formulas so you can do flashcards, do whatever you need to do, but you're going to need to know them. And then n is the nth term, so that's the same. R is the common ratio, which we just talked about in the last video. And A1 is the first term of the sequence, which is still the same. We're going to start off with find the sum of the first 5 of this geometric sequence. You can see that it goes dot, dot, dot. We know that it continues. So what I need to know for that formula is the A1 and the R and then the N, because this is partial sums. This continues on, but we are not wanting to continue it on. So the first 5 terms, be very careful, even though it has 1, 2, 3, 4. It has 4 terms, but I need the first 5. If this helps, this is your A1, A2, A3, A4, dot, dot, dot. Do I need to find the 5th term? No, that's not what I need. I need A1, I need R, and I need N. So my A1 is really nice. It's 1. My N is going to be how many terms am I summing this up to? Well, that's 5. I want 5 terms. And then lastly is the R. Well, I need to find the R. Remember above how we find the R. Well, the R is going to be any term and its predecessor. So the easiest one to see is A2 divided by A1. Well, that would be 0.7 or 0.7 divided by 1. It's going to be 0.7. I now know my R. Do I need to confirm it? If you question your math, do A3 to A2, do A4 over A3, whichever you want. It doesn't matter. Now, just let's plug it in. So I have S, the sum of the first 5 that I want in the series, is going to equal my A1, which is 1, times 1 minus R. R is 0.7 to the n power. Well, that's 5. All over 1 minus, again, the R. So that's 0.7. Now, most students can get to this point, but this is when we have issues. So how you plug it into your calculator is important. If you want to do it in steps, take this to the 5th and then subtract it from 1 and have the number, and then this one have the number, you can do that. This one being there's only the 1 coefficient, you can actually block it with extra parentheses when you put it in your calculator to guarantee it. All depends on your calculator itself, which one you get. So this should equal 2.7731. I would recommend that you get your calculator out, make sure that that's what comes up before you go on. So let's look at the back. We now get to deal with what is called infinite geometric series. So infinite means that it's a partial sum. We learned about that. But infinite is when it either goes towards what is called converges or diverges. So let's just look at this first series. It was given. The series is, and it says, I'm going from 1 to infinity of my function. So this is, again, the beginning. So that's the lower bound, the beginning. And this one is the upper bound, just as a reminder, that's where you're supposed to stop. And this is the function. Well, we can't really stop at infinite, but we're going to talk about how that works. As we put in the first few numbers, if my lower bound starts at 1, then I put that in, I would have 1 over 2 to the first, which is 2, and then I would have 1/2. This is already done for you. You can see some at 2, some at 3, some at 4, ... We can continue on. But notice what happens. As n, that means that exponent, in this case, I labeled it k. So let me say, or excuse me, I didn't. That's in the function, but yeah, we can say as k, because that's how I use the labels, gets larger and larger, we are adding more and more of the terms in the sequence. Well, intuitively, as n gets larger, the sum gets closer to the sum of the series. Okay, so the sum will become closer to the sum of the series. Now notice as n gets large, so 1 over 2 to the n gets closer and closer to 0. As it gets really, really large, it gets closer and closer to 0 because of the fraction. Well, let's look at this. The sum of the series of the geometric gets closer and closer to 1 minus 0, which equals 1. And we use this notation as the sum gets closer to 1, as it indicated up here, that occurs as n gets closer to infinity. So we have two things that happen. Therefore, if the sum gets close to a finite number, finite means an exact number. Maybe that exact number is, the 1, 1/2, anything along those lines. That's an exact number. As n gets large, we say the infinite series then converges. Converges is when they come together and gets closer to a spot, a point. And that would be a finite number. So as S is called the sum of the infinite series, if an infinite series does not converge, then it diverges. Well, if you can't come together, you're going to actually go apart. So converge, come together, and then diverge, they actually grow apart. Well, here's how it gets laid out. If the absolute value of the ratio is less than 1, the infinite geometric series will converge, and you can use a sum formula, which is super simple, to find the total sum. That's where it would converge to a location of a finite number. That's only if the absolute value of R, the common ratio, is less than 1 of a infinite geometric series. And if it is greater than or equal to 1, then it will diverge. And there is no finite spot to find it. We're going to do one example about that and be done. So let's look. Find the fraction that represents the rational number of this item. Well, that seems arbitrary, but let's break it down. So we can write as a series. Well, how we do that, look at the repertain bar. That means it repeats and repeats and repeats. So if we look at it, it would be 2.3, and then I have 5, 1, 5, 1, 5, 1, 5, 1, and so forth and so on. We break this into two sections. You can see where it repeats. So I'm going to draw a line and a line for every repeat and so forth. And I'm going to turn the beginning piece into a fraction. So I would have the beginning that doesn't repeat is going to be 2.3. Well, 0.3 is in the 10th spot. So we would convert that to 2 3/10 as a mixed number. But I need to convert to improper fractions because we don't use mixed numbers anymore, hardly ever. And for those that don't remember, I would take 10 times 2, get 20, and add the top. So that makes it 23 over its original fraction pieces, and that's 10. Now I'm going to take that for the next piece is the repeats. So I would take, what we're going to do is we're going to take 51, convert to a fraction over, which is over each position. So that's over each position. And what that means is what position does that 1 end? That's why I cut it into sections. I would have 51 over, this is tenths, hundredths, thousandths. So remember my first piece of this whole item was 23 over 10. That was the first piece. I'm going to draw my line. And this is going to add, well, it's 51 over 1,000. So 51 over 1,000. Then this is, again, 51, but what's the last position it lands in? That's 100,000. So plus 51 over 100,000 plus 51, and notice that that adds 2 zeros. So I would have, instead of 5, I have 7. 1, 2, 3, 4, 5, 6, 7, and then you know it's over 10 million. The comma goes here because maybe you get off by just counting. Well, look at the pattern and see what it does. Every 2 places goes 2 items. Once I have that, after the first terms of the series, it forms a geometric. Notice that this, and I don't have to go any further. Once I have 2 of them that repeat, I'm good because that will allow me to find the ratio. This is now a geometric sequence, or excuse me, not sequence, series. And it has the dot, 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 because it's a repretend, so it is an infinite geometric series. It keeps going. Well, with that, I can find my A1 of that series and my ratio of that series, because that's what I need for the formula that has been already given to us. Okay, so A1, I'm only looking at the infinite geometric series part. So my A1 is going to be 51 over 1,000 in this series. My R, take any position in the series, divide by its predecessor. Well, I prefer not to deal with the larger denominator, so I'm going to take A2 divided by A1. So you have 51 over 100,000, which is divided by the fraction of 51 over 1,000. Well, copy dot flip. So 51 over 100,000 times 1,000 over 51. Reduce, please, first. You can see that there's 3 zeros, 1,000 goes into 100,000, leaving 100 of them. Those 1 over 1. So I have a fraction of 1 over 100. Please don't put 100. The 100 is in the denominator, so it needs to stay in the denominator. And then on top, it's 1 times 1. Now, my form from before indicated how to find it. And that is my A1. If it's an infinite geometric series, I have A, which really is your A1. Let me just add that little 1 in there. It's the first position in that series. So I have, because I'm asked to find the fraction that represents the rational number, I need to find where it converges. I need to find where that finite number is. So I would take the sum equals 51 over 1,000, that's A1, over 1 minus R. Well, R is 1 over 100, 1/100th. Well, let's reduce. This is 1,000 over 1 minus 100th. That would be 100 over 100 minus 1 over 100, which is 99 over 100. Copy, dot, flip. 51 over 1,000 times 100 over 99. Reduce as much as you want. And I have it all the way down to 17 over 330. Because both 51 and 99 can be reduced by 3. So these are reducible by 3. Gives me 33 here, and this one gives me 17. These 2 zeros are gone, and you can see what happens. Now, that's just the geometric series part. That's this piece. So my final answer has to be the first piece plus the second piece. Well, let me put that in. Final. I would have the first piece, 23 over 10, plus the sum of the geometric series, or excuse me, the infinite geometric series, and that would be 17 over 330. Well, we got fractions. Get a common denominator and add it up, and you can take this, divide it. I'd actually multiply that by 33. This becomes, let me get my other pen back, sorry. This would be 759 over 330 plus 17, if you have to do it by hand. Of course, calculators do a lot of this work for you, but this would be multiplied by 33 over 33. Add those together. This becomes 776 over 330. Well, they both end in an even number. I know that it can be reduced at least by 2. And I have that reduced, and that would equal 388 over 165. Now it doesn't reduce anymore. That's as far as it goes, and that would be the fraction that represents the rational number. So remember, if it's a repetant, it's going to repeat. There's going to be an infinite geometric series. You're going to find that piece separate from the piece that does not change. And then you take those two pieces and you're going to add them together. You got to find the sum, though, first of the infinite. And that's because of that. Hope that helps. Have a good day.